Hello, everyone, and welcome to the Hyperthesis podcast. Thank you so much for joining us for this very special episode. I'm Patrick.
I'm Liam.
I'm Feely.
And I'm Parisa.
So, as you can hear, we do have a special guest on for this episode, and we figured after 10 episodes, we might do something a little special. So, joining us today is Parisa Nozari. She is an astronomer at Queen's University and is currently studying space dust and different astronomical phenomenon. So we'll be asking her a lot of questions about astronomy and science and just anything we can think of. But before we start that, we'll discuss a few things that we discovered within the past week, whether it's new or new to us.
All right. I found this article that's just got published a few days ago. It's on a breakthrough in quantum computing. As we know it, the infrastructure of computing these days are based on silicon, and silicon has, very versatile properties that works for computers, making transistors and making gates and whatnot. And for quantum computing, is a little more complicated. So actually, the researcher, I think at Simon Fraser, has found they call it a missing link in silicon or in the structure of silicon that actually gonna helps basically makes quantum computing more efficient, more accurate or whatnot. We'll actually have to read more on it. But yeah, if someone interested, so just probably can Google it out.
Yeah, it seems like in particular, this is more useful for interconnectivity between quantum computers. So instead of just looking at a single isolated system, this new discovery and new research that's going on with this silicone, what are known as T centers, can be useful for actually transmitting information. So traditionally, we transmit information between computers either over signals that are carried by a wire or through light signals that are carried by fiber optics. So for example, if you're with TELUS, they have their fiber optic network, which transmits signals using light. And that's how most telecommunications worldwide behave. I guess there's an increased amount of satellite communication, especially with commercial satellite internet becoming available. But the idea of transmitting information over cables is very important and it's very fast. And so finding better ways to actually connect quantum systems and I guess look at quantum methods of transmission further enables not just a single quantum computer, but the connection of many computers together.
So, when the big problem with quantum computing, I think, is decoherence, right? So basically, if you're trying to send a quantum signal or something like that, it'll get affected by its environment and then collapse to a certain state, and then you no longer have your quantum state, and things become classical again. So in the abstract of this paper, about this article that you're mentioning, it mentions something about how they want longer lived kind of signals. So how does the silicon come into play for creating these systems that last longer and don't decohere?
Well, if we think about coherence in terms of, you think of lasers and stuff, right? Some lasers are created from some crystal, and those material actually helps regulates coherence. And if they can find a way to create signal through silicon, I think that what they say the T centers thing, such that the coherence length is long. Maybe that's the way, or maybe the T centers means they can just split the signal while maintaining coherence.
Okay.
It's also interesting their use of silicon because I don't know too much about quantum computers, but I'm pretty sure silicon and other such semiconductors aren't as popular for the actual quantum computation themselves. They tend to use materials that are easily supercooled, if I'm remembering correctly. And so the use of silicon, which is a very common element and is also already mass produced in, well, very large numbers in every computer, and we can also get it very pure. So seeing such a common material being used or having the possibility to be used more widely in quantum computation systems is very interesting. And it will be interesting to see if we can develop methods from what we currently have to essentially change our use of silicon.
Yeah, and in the article, or at least the paper that the article cites, they mentioned that silicon's ideal for this because of what you said. It's commercially available on industrial scales. So we got to get the quantum computers working, but if you can get them working with silicon involved, then that's a good thing. It's not this very, very expensive element that you have to spend a lot of time to create.
Silicon may be available, but the ultra cold cryogenics may not.
Yeah.
I mean, it's going to be still difficult to make quantum computers anyways.
I guess we're still vying for that room temperature superconductor that we've been promised for many years, but yeah.
Yeah, it's funny because when a lot of physicists talk about high temperature superconductors, they mean like 80 Kelvin or something like that. So we still got a long way to go.
They can have room temperature superconductors, but the pressure has to be ridiculous, right? So you can have room temperature superconductors, but the pressure it had to operate at is just out of this world, literally.
Just to touch on superconductors, just because they are fascinating and important for the future of computation itself, is the fact that there's been a movement, especially within the past 20 to 30 years, of finding superconducting materials based on experimentation and chemistry to now there's definitely a lot more papers coming out and a lot more research going into computationally finding the best combination of elements to make superconductors. And I remember reading a paper quite recently that was detailing how we can use machine learning methods to essentially sort through many different types of superconductor material combinations to get those higher and higher temperatures and better performance.
One other thing to mention just before we move on is that if you want to read more about this, the article cites a paper from Nature called "Optical Observation of Single Spins in Silicon." So, if you want to look into that, that's where to find it.
All right. To move on a little bit, just give Parisa some of the floor. So, Parisa studies space dust as I know it. Maybe the proper names or terminology that's more fancy, but because I don't know much about it. So I've asked some preliminary questions. So, Parisa, what makes you interested in astronomy in general? What's inspire you?
Well, so hello everybody. Thank you for having me actually. But I don't know. I was one of the luckiest one that I just like decided to do astronomy when I was a kid, and I just keep going, and then continue. So, yeah, I think I was like interested by when I used to go to stargazing and then with my family, and wonders of night sky always amazed me a lot. So I just decided to just do physics first of all, and then I ended up, in astronomy. And to be honest, first of all, I was not particularly looking for star formation and dust grains specifically. I just wanted to do astronomy, and I ended up starting my research in dust grains, but it quite amazed me a lot. So I love it now.
So can you tell us about your research? What are you doing exactly?
Oh, yeah, for sure. Actually, I'm specifically working on star formation, ISM, because our environment, I mean outer space, is not quite empty. So and interest in the middle of the stars, and then those galaxies, we have a bunch of dust and dust grains. So if you know the Orion constellation, which most people call it like winter maker, which is quite obvious in wintertime. So I'm specifically look at the specific part of the Orion constellation. There's a molecule cloud. So we see a very strange evolution in dust grains, which is not quite common. So I'm particularly looking at Orion molecule cloud and then study dust grains and their evolution. And I can tell you more about it later. But because those are the dust are responsible for making the stars, and their lifetime, their evolution is quite important for us to know the star formation. And people usually hate dust. It quite offends me, but it's like true because dust also are responsible for making stars, but at the same time, they block our views of looking through objects like galaxies, stars. So most of the people, most people like hate dust because of that. But actually, they're quite important for making those all objects that we are currently study them. So yeah.
Well, the two things. First is you mentioned the term dust grain. That's not really commonly used. Can you explain more of like what's dust grain?
Because actually, that's the difference between dust and gas. Because gas, they're kind of bunch of molecules or atoms or a bunch of things, but dust is actually a real thing, and which I'm telling you, like, much bigger than gases. And they're like grains, because when I'm saying you big enough, I mean micron size, but they're literally the silicate. So they're like sand size, and usually the component of sands, but they're like very, very tiny, but they're like dust grains. So you can calculate, I can accumulate them as a bunch of like sands or something, but in micron size.
Mike, I have a question. So when I took a fluid mechanics course a little while ago, and the guy who taught it was an astronomer, because there's lots of fluid mechanics in astronomy. So when I think of gas and liquids, I think of fluid mechanics. But do these grains, or do you describe them with fluid mechanics, or are they a little different because they're so big?
When I'm saying so big, I have to mention that micron size, but they're like solid.
Okay.
And they can vanish or become a gas after a lot of interaction happening, but originally they're solid, and then dust grain.
Okay.
As a follow-up question to that, from what you said earlier, that these collections of dust go on to make stars. From my very limited knowledge of astronomy, stars are mostly hydrogen and a little bit of helium. So is it these collections of dust that are forming stars, or is there a lot of hydrogen mixed in there too, and just free helium and hydrogen that are also coalescing into stars, or is it a lot of dust actually in there?
Okay, let me start with a story. Actually, it's a kind of interesting loop happening in the sky. So first of all, just imagine that first of all, we have like a star dying. So when a star is dying, it kind of like very huge. There's like a bunch of ways that star can, ended up their story with. Like it can be black holes, nebulae, or but in all those scenarios, we have like a very huge shells that just like expand into universe, like so it just like expand a lot of dust grains and materials that explode away. So we have a bunch of like materials, dust grains, and all those components. So, and then they build a molecular cloud. So in the molecular cloud, it should be very, very cold. Unless, the stars are like pretty hot, and then they have a very dynamic environment for making the stars. But the environment for stars to be born should be extremely cold and at the same time very dense. So these are the bunch of things in molecular cloud, interstellar medium, atomic hydrogen, molecular hydrogen, and the dust actually are acting like environment for this molecule, for atomic hydrogen to interact to another atomic hydrogen and make a molecule hydrogen. So and then those dust actually coagulate to each other, and while gravity wins and like a spot in that molecule cloud, which is like very dense and filamentary, so much structure in it, and suddenly gravity wins out of pressure. So a core going start to happening, and then more and more, and then accreted, and then actually a star born. So actually, a star is born when another star died in the past and explode those material, and that's kind of loop and happening. So let's just make it a little bit fun. Actually, it does kind of acting like a dating app. Like, just imagine that a person want to meet another person, and then there was like kind of platform for them, like I don't know, those like apps, and then this does is literally act like these kind of environment, and then make those criteria just like be with each other, and then everything be in a correct actually situation in a correct moment in the correct values, then a star going to be gravity wins and the star born.
Very cool. I've never heard of, I guess, a dating app used really in any physics analogy, so I may steal that one in the future. Just to put some, I guess, approximate numbers to things, you mentioned that things need to be very cold and pretty dense. But how cold is cold and how dense is dense?
Oh, actually, when I'm saying dense, it's not that dense. It usually like 10 to 5, and like the density would be 10 to 5 electron per meter squared, per meter cube, I think. Yes. So it's like very diffuse for us, but it's like pretty dense for the environment. And the cold should be like approximately about 10 Kelvin. So yeah, that's kind of criteria for those molecular cloud.
Yeah, so it's fascinating that people think of it just by looking at the sky. It's like, well, I see some dust. Now I could see accretion. I see this creation of stars. Like, from what?
Yeah, and then it's very interesting because like actually a core that the stars need to be formed within, you cannot imagine how big is this. It's like 10,000 times of the distance between Earth to Sun. It's the environment of the core that needs, all those micron-sized dust needs to coagulate together in that huge, enormous environment for a star to form, at least, which is quite impressive because I'm actually studying a tiniest scale in astronomy rather than people that study cosmology, galaxies, or like 10 a parsec or something. I'm studying 0.01 parsec, and that is 10,000 times of the distance between Earth to Sun, which is quite insane. So just a very fun fact that I wanted to mention.
Yeah, these astronomical scales are mind-blowing. Sometimes I just sit there and think about how far and how big things are, and it's very kind of scary to think about sometimes. So I wanted to know about the time scales over which these stars form through these clouds of grains. Says they're really big, like multiple times the distance between us and the sun. But how long do they take to kind of once gravity, I guess, takes effect? How long does it take for things to come together?
Oh, actually, it's not a pretty early process. So it's like 100,000 to
Hmm.
million years. It takes time for those grains to just like form stars. And actually, the lifetime of the different type of stars are different. The more massive they are, the fastest their lifetime will be, and vice versa. So
Yeah. How about the length scale? You said a parsec. How long is a parsec?
I think we can do simply a math here. I don't have it on top of my mind, but I think if just like 0.01 parsec, which is like 10,000 AU, and 1 AU is like the distance between Earth to Sun. So like it's kind of each parsec, it's kind of like 10 to 6 times of the distance between Earth to Sun.
Because I'm curious, because like the AU makes sense, like astronomical unit, distance on Earth to Sun, but parsec is
Actually, I think parsec makes sense too, because if you wanted to just like describe the galaxy scales, you cannot use any
light year.
light. Oh, light. We use. I think it's parsec and light year has some relation to each other, but I don't have it in top of my mind, to be honest.
So just as a bit of background about the parsec, so it is 3.6 light years, and so light year is the distance that light can travel in a year. And the parsec was first used, I think the technical terminology is, it's the length in which 1 AU, or the distance between the sun and the earth, subtends 1 arc second. So to make that a bit easier to understand, if you were really far away and you were to have a little scale that showed arc seconds, so a division of a degree, and then another division of a degree into arc minutes and then arc seconds, if you were to be far enough away that 1 AU covers that 1 arc second, then the distance between you and that object, where that, or that very long line of the value of 1 AU, that distance is 1 parsec. So for reference, our nearest star system, Proxima Centauri, is around 4 light years away. So it's just a bit further than 1 parsec. So it's a very big distance.
Yeah, it makes more sense now that everything in polar coordinates, right? In arc and stuff. Yeah, now parsecs makes more sense.
So going back to the formation of stars, are these same grains of dust that eventually go on to form stars, are they also responsible for the formation of planets?
Oh, yes. Because actually, when the star forms, there's also, for example, just imagine there's like a lot of dust grains coagulate to each other and then, making a core. And then in that middle of the core, a star born. So, and actually, there's a lot of materials still not turned to be stars. So those are that actually gravity winds forming the stars, but there's also another material. And because this is like a huge object and rotating around each other, it creates a disk around it. So in every single star that is born, there's a stellar, I think we call it protoplanetary disk. Yeah, protoplanetary disk. Rotating around the middle stars and the core. And in that disk, there's also dust and atomic hydrogen and molecular hydrogen. And this is the kind of same processes happening for the planet. So in that dust rotating around the core, in the spots that gravity wins over the pressure, we have another object, and that object will be planet. So the process is quite the same, but I think there's a lot of different details about it, and you can ask disk people about that because they're particularly study about planets and how they form. But as actually the terms like quite confusing because they call the star disk like protoplanetary disk, which is I was confused at first, but yeah, because the planet formed within that disk rotating around the star.
Okay. So as a follow-up question to that, what helps define how much dust goes into the formation of the star versus the formation of the planets? And what dictates the eventual size of the star once it's formed?
I think actually I'm not a kind of expert in that and the star formation, the stars specifically, but as my understanding was that there's a kind of pressure happening in the middle of the stars that acting against the gravity. And once that pressure and gravity reach to a balance, it's the dust stops accreting to each other. So that's where you stop accreting the dust grains, and then they just stop accumulating, just like accreting to each other. And then that's where, just like define that, okay, that's the new star, and then the process stops. So for the planet, it's like kind of the same process, but the big difference between stars and planet is that stars, like the hydrogen in the middle of stars, starts to diffuse and starts to burning. But in planet, we don't see this. We don't see this process, and we don't see any molecule hydrogen or atomic hydrogen diffusing. So that is the difference. But about the size, to be honest, I cannot tell exactly.
Well, people who study solids and liquids and fluids and stuff, when you do molecular dynamics and whatnot, what you can see is the phenomenon of nucleation. I think this probably happened this too. Like it has to be certain size for it to coalesce into a planet or a star. And I'm pretty sure they do research on this with basically the same or similar techniques people use in the thermodynamics or statistical mechanics to study this, because at the end of the day, even though they have a different length scale, what they do is instead of the Coulomb interactions, they have gravity. And it shouldn't be too hard to switch the interactions and see how the simulations go and whatnot.
So how do you research this? Do you do theoretical stuff? Do you go out and look through telescopes? Do you use data from other people's observations?
Well, actually, thank you for asking this question, because as I said, we cannot see dust through the optical telescopes. Because optical telescope, the objects should emit lights that we can, detect it with the optical telescope. So we need the radio dishes like interferometer. So one of those huge interferometer was like ALMA in Chile, and one of them is like NOEMA in France, which I'm working with. So actually, we wrote a proposal for NOEMA, and then they kind of did the detection for the specific part of the Orion Nebula that I wanted to study. And they provide us with the raw data. So actually, I am kind of observational astronomer, that I'm having my own data from the telescope that I wanted, and then I analyze it, do all of the data reduction all by myself, and then extract those values that I needed to know, and then and then do my research with those data.
Cool.
So and then and I think that's quite interesting to mention that's interferometry is kind of the thing that JWST is doing for us right now, and that's quite impressive because most people thought that this is kind of the new telescope instead of Hubble, but it's not actually. It's like a great complementary. So yeah, that's why we can see a lot of details and dust with JWST as well.
Cool. How do you use interferometry to how does, because when I think of telescopes, I just think of some wavelength of light comes in and focuses, and then you get data and you do data analysis and make some plots. But how do you use interferometer to get measurements of this gas or these grains?
Well, that's how interferometry work, right? There's light in, you put in some kind of prism or separate into different spectrum. So if you have some kind of light input in, the interferometer takes that light in, right? Like that data, and basically, either spread it out, so different spectrum, to see the relative intensity in each spectrum. I think that's what our former colleague Heather researched, right? Doing what type of molecules or what type of elements are in certain types of stars and whatnot. So those are information from the light that's coming in.
Yeah, I'm very used to, when I think of interferometry, is just splitting a beam in half and then measuring a phase difference. But yeah, okay, I see what you mean now.
So in these signals, so once you've collected the data, whether it's from the Atacama Desert or the James Webb Space Telescope, what do you look for to say, okay, there is definitely dust here, versus, say, looking at just, I know it's very hard to find, but just dark space where there's nothing there. How do you differentiate between the two?
Actually, I think the space is not empty everywhere, but in those where that like you see more dust, it kind of like you can see a very like diffuse or very dense cloud that you can see. Oh, okay, that's the kind of part of the sky that we have some materials more than that. But you can also find atom or molecules everywhere, but they're not quite like visible to you. But for like if you just look at the JWST new images that releases, because I think it's pretty impressive. So in the last image, which they call, I think, the name was Carina Nebulae. You see those like structure, like this is like a bunch of material, like in the molecular cloud. So which I do not believe that is like the space is like empty, but those are like more dense, and then you have a bunch of more materials that block our view sometimes, like a pretty shield or cloud. You can see, oh, this is like interstellar medium, but you cannot see dust grains. You just see a bunch of materials as a cloud.
I feel like the length scales would be so weird to be able to look like very, very far away and be able to identify like a piece of dust.
It is very, I think, it is quite impressive. So I don't know about the technical aspect of this. So, but yeah.
I'm curious, given that these dust grains lead to the formation of stars, are we able to gain any data about them from our own solar system, whether it's some sort of space probe or satellite collecting dust grains or anything? Is there ways that we can confirm what we're seeing in many, many light years away with what we have in our own solar system?
Um, well, I think in our solar system, you can find a bunch of like dust grains from the comets left over. These are like bunch of dust grains, but they're not dust grains. They're like a bunch of silica, which are like part of huge or icy mantles that just like when goes through the atmosphere, it just like they burn it out and then we can see it. But dust grains are like micron size, and I think you can yeah, I think the comet leftover just still in our solar system we have the Kuiper belt, which is have a lot of rocky things, and then we have dust grains, but we don't have any molecular clouds. So to see, because actually the scale of molecular cloud is like pretty like enormously bigger than that, because a sun is one of those stars that are can be formed in the huge molecular cloud, and that create its own solar system and planets over. So just think about it. That's our sun is one of those like tiny typical stars that can be born within a huge molecular cloud. So if you wanted to see molecular clouds, you go to outer the solar system and look at through the Milky Way, or look at it through a very distant object, because while you're just like this, while you're sitting in this room, you cannot see the room from the other perspective. So you have to get out of your room and then look at, for example, like the door, um, from the other direction.
Well, it looks like the solar system was just a part, like a small part of the dust cloud, and it was formed.
Yes, when you just if you just quickly look at the Milky Way, and then just see where are we, you can see, oh, we are kind of like in the very cloudy uh part of the one of the arm of our Milky Way. So I don't see if there's any particularly molecular cloud that we were sitting in. But we definitely were sitting in one of the molecular cloud that might was existing before, but maybe it just like goes away by a different dynamics that happening in the space, like shocks and winds and then all the other stuff. just like blown away. But or maybe we are still in some specific cloud. I don't know.
Do you say sharks?
Pardon?
Sharks and wind?
The shocks?
Oh, sharks.
Yeah.
I thought I heard sharks.
No,
Like-
shocks.
Space sharks. Ooh.
Yeah, because if I thought before the space was pretty empty and stars, just a bunch of stuff just forming, but it sounds more like there's a bunch of almost like a sea of molecules around, and these stars are formed by, well, if part of it's become dense enough, is condensed into a celestial body, and those dust just move on. Huh.
Exactly. You can see definitely what you already said in the last image of the James WST image, which it's like Carina Nebulae. It's they call it cliff and mountains, but you can just like visualize it as whatever you want, like a sea.
Yeah, because the solar system that we are in now are pretty empty, you know? Like, I mean, we don't have that, well, as dense of dust cloud as what we see in some of the images.
And I think all the dust all the dust that existed before ended up being something in our solar system. So all the dust could have ended up being stars or planet. They already like formed a planet and stars. So yeah, I mean, in middle we're kind of not that like dust things that can be formed. Another celestial object in our solar system.
I've heard of these things called plasma lenses in astronomy. Where basically, like you said, this dust it'll affect your measurements. It'll get in the way of things, and I'm assuming that's because as light travels through it, it refracts and it can be absorbed and emitted, and all kinds of wild stuff can happen, I imagine. But is this related to plasma lensing at all, or is that just completely different? Because plasma lensing is something to do with the interstellar medium, and you can kind of amplify signals by lensing them through refraction somehow.
Well, I don't know that much about plasma lensing, and I
Okay.
think that's a different thing. But I think it's kind of part of, the observatory method that they use, but not sure about
Okay.
this.
I think we mentioned before that James Webb is an infrared telescope, right? So it should probably see more of dust and all these hidden parts than Hubble. Because I think Hubble use different range and also probably have part IR, but James Webb is strictly mostly IR, right? So in terms of your research, is that like exciting to see those terabytes or petabytes? I don't know, like so many bytes of data coming in.
Yeah, for sure. I think that's why NASA just call it as a great complementary rather than just like a telescope instead of Hubble, because Hubble operating visible lights and also UV. But James Webb is like interferometer, which literally means with James Webb we can see those objects that we couldn't see with Hubble, because Hubble detect the lights coming out from the stars or bright objects, but interferometer just like a laser just goes through those cloud and dust and then see beyonds of that, or even can be able to map those molecule clouds or like those very impressive details out of everything. Because as I said, the reason why most people hate about that is like block our view, but because of their thickness, in astronomy we call it optically thick. But James Webb can be just like goes through it and then just show us beyond what we used to see, and then also detect more distant the object from our early universe, which is quite impressive. So if you ask me if that's kind of interests me or not, just look at those last image of the JWST, which you already call it as like an ocean. So this is kind of the field that I'm looking at right now in Orion Molecule Cloud, but I think this is in a different constellation. But yeah, people that are interested in star formation, ISM, interstellar medium, this telescope is like big difference.
Yeah, one thing about I always hear people saying, you see through, but it's not what really happens, right? Like the telescope just sits there. The photons are already there. So what actually happens is your instruments become more sensitive.
Exactly.
Or be able to select or pick and choose the data. So it's like, in a way, it's not really seeing through. It's just collecting things that are already there that we weren't able before. Like, when you take a magnifier, it's not like you're seeing through the table. You just see something that is already there, but don't have the resolution or the sensitivity. Yeah.
Well, yeah, actually, you're right. We physically don't see through, but for when I'm saying that Hubble was like just sensitive and visible range, it means that Hubble could detect the light emits from the celestial object, but actually JWST is sensitive through the like temperature, even the temperature of those dust grains, and that's why we call it interferometer. Like if because those objects are kind of like hot a bit or emit a bit heat, so when they just like emit heat, it just can sensitive to that heat as well, because those have some wavelength and JWST is like more sensitive to that wavelength. And then that's why we can see beyond, because we're sensitive to like more wavelength that the object kind of emit a thing.
Yeah. What do you think about the choice of false color they put on these images? Because infrared, the color we see, they're not. No, if you're there, if you can't get there, it's not what you're gonna see, right? You probably don't see anything because they are basically cold dust. So, what do you think about the choice of colors? I mean, they're pretty, but just do they signify anything?
Well, actually, I do believe color are physical and real, because the reason that the reason for why they choose different colors for thing is just because by due to spectroscopy and then analyzing the data, they can know what kind of component do we have in those like objects, and for each component, we have a color for that. So they just like set a different colors for different materials and then different component. But for like galaxies, the colors usually indicates the heat. So for example, the red one are like the cooler one, and the blue ones are like the hottest, the hotter object. So the colors sometimes indicates different thing, because for those thing that we don't see it in the visible light, we cannot define a color for that, but we can define a different color for showing different things like their temperature, their density, or their component.
Yeah, that's exactly what I was going to add in. Is that I guess it depends what you're looking for, depending what color you want to give it, right? Like certain wavelengths, certain densities, distances, all kinds of stuff you can choose from. Just depends what you're looking for and who you're presenting to.
Well, it feels uncommon. You said that when it's cold, it's red.
Yes, it is. It is the uncommon thing in astronomy, and in astronomy, sometimes everything is like kind of reversed, which is like, well, I don't know. This is the way that astronomer used to do. But yeah, we choose red color for the cooler object, and then the blue one for the hotter object. But that makes a bit sense, because blue, it's like the blue has more energy. So it's like, and the red has like the less energy, and very basic physics. So it's like, okay, but the object is hot, so it like have emitted more energy and then more active, and then so okay, let's indicate blue for that. But I don't know why on Earth we decided to set blue for cool things. That's, I think, it's strange for us.
Yeah, I imagine they did it based just on physics, right? Like when a hotter star is more blue than it is red, kind of thing. Like you said exactly.
Well, but in terms of daily life, right? What you see as cool stuff are water, the ocean, fire, red is hot. So it makes a lot of intuition, right? When you see something red, you think of hot, even though the physics tell us the energy for ultraviolet or violet or the purple is high energy and red has low energy. And you can feel that too. If you turn the light in your room red, it's like it's fine. But when it's like blue, it really hurts your eyes. That's why the blue light kind of messes with your sleep.
Yeah, well, again, I guess it comes back to who you're presenting to. So maybe the Hubble images they gave to the public, maybe they could have made colder things blue and hotter things red. But if you want to present them to physicists, you might want to make the hot things blue. I mean, I don't know what they did, but
I know that color representation is a hotly debated topic, whether in astronomy or just trying to show off a nice plot. And I know it's a debate I've had a few times with some colleagues, whether it's showing height or whatever. So if you have color map input, feel free to message us.
So yeah, as Felix said, when you turn on the blue light, it hurts your eyes. So like more energy. So it can be hot a bit. So I'm just a fun fact. That's why we do use a red headlight when we go to stargazing or want to do astrophotography, or while you operating observatories. You usually turn on a very dim like red light all over the observatory, and then mostly the domes are kind of red colors, just because of that, because it just hurt our eyes less energy.
it's also most people's glasses have a blue light filter on them, so that less blue light goes into your eyes. And that's it's very useful if you do what I do and stare at computers and TVs all day. But yeah, same principle.
Yeah, actually, blue lights don't damage your eyes. If it really damaged our eyes, we would have
Yeah.
an epidemic of blindness. But it does mess with your sleeps a little bit, Yeah, but my glasses don't block out blue lights, because if you block out blue lights, your color perception would be different. So if you do photography or anything visual,
Yeah, so like my glasses have this blue light filter, but it doesn't completely filter out blue light. It just filters out like a small amount of it. But even when I put my glasses on, the whole world becomes slightly more yellow and more red when I put these glasses on. So it does change your color perception because it's filtering out some of those wavelengths of blue light.
So moving on from blue light filtering, just a couple final questions. But where do you hope to go with this research on these dust grains?
Well, actually, dust grains, as the same as the other celestial object, has their life evolution and life process, and there's like kind of different things happening with them. So this is this thing that I wanted to end my talk with, that actually dust used to grow, which is very interesting, because if the supernova or those dynamic event in the sky can only destroy 40% of dust, and we recognize this by looking by the observation, and we figure out, oh, if all the dust have been destroyed by those like very dynamic things, so we shouldn't have that much material left in the space. So by just like comparing the data, we realize that, oh, the dust should grow in size and also coagulate together. These are the same thing that should happening at the same time to star form. So what I'm doing is like, we're looking at the very specific filament at Orion, and that dust grains there showing a very enormous and unusual growth in size. So which it's not quite usual for molecular cloud or filament tree structure scale. So we used dust grain growth in core because that's the part stars usually tend to form, but it's like kind of uncommon in the molecular cloud size. So what I'm doing is that, compare the data, do a lot of analysis to figure out if is it a real things happening, or no, it's just because of the lack of the observation or other effects that that we see such a thing through the observation. And if this is something real happening, and we see, oh, it's not because of the other thing, it's just because of the dust itself, and it grows in such a scale, it's kind of the event that never have been seen before. And it's kind of quite impressive and maybe change our perspective and understanding of like dust evolution.
Yeah, I mean, good science, we study anomalies, right? Try and find something new that challenge the status quo, find this instability in the current theory and just find a new thing. And I thought we figured out most of the stars formation stuff, but apparently there's more.
Yeah, it's always more. So I think that's the cool part of the science that you shouldn't have. We build a model and we work on it. We observe a bunch of things, and maybe those kind of prove our models and theory. And suddenly you're just looking at something else, and oh my gosh, it's like totally a different thing happening there. Is that okay? Is this a model correct, or maybe you have to recreate your model or change your theory? Because I'm kind of observational astronomer and I'm not a theorist, so that's why I'm just looking at the things and let you guys theorists know, oh, maybe your model is not correct.
So that's usually the case, I think, right? Is that like you always start off with a simple model and you're like, all right, it works pretty well. And then you notice, oh, there's a couple blips in the data in this regime, so we got to modify it. And then you get more observations and you notice, well, in this scenario, it doesn't work, so we have to improve upon it there. And then eventually you get a really good theory, but it takes a while.
Well, that certainly sounds very interesting, and hopefully you get some very nice results from observing these anomalies. So to everyone listening, just keep an eye out in the next year or two. Maybe we'll see a publication or a groundbreaking discovery about how these dusts collect and form and grow. So I'd like to thank you very much for joining us on the episode today. It's been a pleasure having you as a guest and learning all about these interstellar, or I shouldn't say interstellar, but stellar creating dusts.
Thank you so much for having me, and yeah, that was my pleasure too.
So I think we're moving on to the last part. So Patrick has prepared some story about measurement and uncertainty. But before that, I'll let him talk about how to contact us.
Well, if you're listening right now, chances are you found us, but just in case you want to share the Hyperthesis podcast with your friends, families, random strangers on the street, you can find us at Google Podcast, on Apple Podcast. We're based at anchor.fm/hyperthesis, and you can also find us on Spotify. If you would like to reach out to us at all, you can contact our Gmail address. So it's hyperthesispodcast@gmail.com, or you can reach out to us on Instagram at the Hyperthesis. Feel free to send us a message. And if you are interested in being a guest on our show and talking about your research or area of interest, feel free to send us a message, and we would be more than happy to have you on the show. So try and find us and reach out to us. Moving on to the story today, I'll try and keep it nice and short and sweet, but it's an issue that scientists everywhere, not just physicists and astronomers, but everyone has to deal with at some point. And that is measurement and uncertainty. So any measurement that anyone takes will have some sort of uncertainty to it. Whether you're trying to measure the length of a board of lumber that you're cutting for a project, or trying to define the mass of a kilogram, all these different measurements that we take will have some sort of error to them. So for example, when you're measuring a piece of lumber with a measuring tape, you may say, okay, this is 1 meter long. But you can get a little bit more accurate than that, saying, okay, so it's 100 centimeters long. And maybe you can tell to the nearest milliliter how long that piece of board is. But you can't tell for certain the exact length of that board. There will always be some sort of uncertainty in your measurement. So these uncertainties in measurements are prevalent everywhere. So, for example, if you've ever done a physics lab, whether in high school or in university, you know that, say, if you're trying to measure the distance a ball goes when you throw it, you can definitely calculate it based on the initial velocity and its trajectory, how far that ball will go. But to actually be positive about where it goes is essentially impossible physically, because if you're measuring the initial velocity, then you don't know that velocity to the infinite number of decimal points. And so uncertainty is prevalent, and it's very prevalent everywhere. So as a very interesting example, when you try and measure the coastline of a country, let's say, for example, Australia, if you were to measure the coastline of this country, you would say, okay, so if we make a straight line from one point on a beach to another point on the same beach, let's say that line is 2 meters distance and it's right against the water, and you do that for the entire perimeter around the country, then you can say, okay, we have a definitive coastline for Australia. And let's say it's something like 25,000 kilometers. So if you want to walk all the way around Australia, you would have to walk for 25,000 kilometers. But in reality, the placement of, okay, how big is that line and where are we placing it? Is it right against the water, or is part of it only against the water? This leads to uncertainty. And so a very interesting thing is if you search up right now on Wikipedia the coastline of Australia, it will come up with a chart. Canada is actually number 1 for longest coastline on that chart. Fun fact. But you'll see a couple different agencies that have measured the coastline. And those different measurements for Australia are wildly different. So for one of the agencies, the coastline is somewhere around 25,000 kilometers. For another measurement of Australia's coastline, and it's essentially perimeter, you'll see 60,000 kilometers, which is more than double the first one. And that just comes from uncertainty in how it's measured. And unfortunately, in many publicly available things like in Wikipedia, they don't include the uncertainty in the measurement or even the method. So these differences in how things are measured have to be taken into account. Now, as physics students, or at one point we were all physics students and are physics students, it was drilled into our heads how to handle uncertainty. So if you were in a first-year lab, you would take measurements and include the uncertainty. And you would be able to define your results as being accurate or not based on the uncertainty that you found. So for example, if you were trying to find the acceleration due to gravity, you would say, oh, I found it was 8 meters per second instead of the standard 9.81 meters per second. But that's plus or minus 2 meters per second, so therefore I'm right within the uncertainty of the value that I got. And so as scientists, it's important to be able to measure this uncertainty. So I have a background in particle physics, and to say that you've discovered a particle, you need to be very certain. So in this case, we use the sigma scaling. So it comes from a Gaussian distribution, and I'm sure we'll have a whole episode on it, but you need to have 5 sigma significance that something happened. And so essentially what that means is that, for example, something like the Higgs boson, if you have 5 sigma uncertainty, that means it only has a 1 in 3.5 million chance of a signal that's produced by the Higgs boson to happen randomly. So we're pretty sure that something like that exists. And the recent pentaquarks and tetraquarks that were discovered by the Large Hadron Collider, that has sigma values of 6.5 and 8 sigma, which are just, we are almost entirely positive, but there is still that little bit of uncertainty. Just as one more little story within a story about uncertainty is the invention of the metric system. So prior to the French Revolution and before even Napoleon was very prevalent within Europe, there were many different ways to measure things. And that's not just saying, oh, well, yeah, you can measure a kilogram of feathers by placing them on a scale or by seeing how much water they displace. They had different definitions for the same thing. So a pound in France was different than a pound in England, and a yard in England was definitely different than a yard in France, which is, fun fact, why we think Napoleon was shorter than he actually was. So overall, you had thousands of different measurement systems in place that differed between towns and even if you were on the port or in town. And so to try and reduce the uncertainty that comes from conversion or saying, oh, I have 5 pounds of corn in my wagon, and it's actually 4.5 pounds according to someone else. To try and mitigate that uncertainty and the weird conversions that must have had to happen, the introduction of the metric system happened. So for those of you not in the United States, or I think the 2 or 3 other countries that use different systems, the metric system is quite common. But it had to be introduced and was done so in France and was utilized by Napoleon and his whole regime. And so this metric system is a standard way to measure things. So they're based on different properties of materials originally, but it has moved on to being determined by actual physical constants. But even within the metric system, trying to figure it out, there was uncertainty. So to figure out the distance of a meter, they were trying to measure a certain length along a line of latitude in France. And there was even uncertainty in the measurement of trying to measure, I think, about 1,000-kilometer line, which ran over the Pyrenees Mountains and involved using 4 platinum rods. So there's uncertainty even in the basis of the metric system, which is seen as something that's consistent and universal. So nowadays we have the Bureau International des Poids et Mesures, which is the Bureau for International Weights and Measures that controls all of this. And before our kilogram and our meter were defined by physical objects, but now they're defined by things like the speed of light or Planck's constant, which are constant. Now, there is a lot to say about uncertainty, and I'm sure we could have a full episode or even a full couple episodes related to it, including like the uncertainty that comes from quantum mechanics and how nothing is actually 100% certain for the most part there. And then we could also talk about the entire field of statistics and how uncertainty is measured and calculated and determined. But uncertainty is definitely something that is everywhere. And much like the astronomical observations or observations of acoustic black holes, it's prevalent and something that we need to consider.
Yeah, I think we definitely should talk about it because I have very strong opinions about how math and physics are taught, and the way error tends to be taught is usually quite bad. It's never taught in a straightforward, intuitive way. I find it's just kind of thrown at you from the side, and they kind of expect you to figure it out through weird methods.
But yeah, it's definitely a topic to discuss further. But just to finish things off, I'll end with a quote by Richard Feynman, which is, "What is not surrounded by uncertainty cannot be true."
Good quote.
So thank you everyone for joining the podcast today. We were very thrilled to have our first guest, and we hope to see you all in the next episode.
All right, take care.
See ya.
Bye everyone.